Hello everyone. So we have arrived at the last chapter of this course, that is dynamic fracture. So we have discussed in the last lecture, the earlier lecture about shear bands, and now we will talk about dynamic fracture. I hope that at least some of you have you have taken a course on fracture mechanics, and I know that for the undergraduate students, most of you have not taken any course on fracture mechanics. So we will briefly discuss the very basics of fracture mechanics. So this will be on fundamentals of fracture mechanics, but if you are more interested to learn about basic fracture mechanics, I would suggest some books. Please go through it. So the books by Anderson, or this is for fundamental of fracture mechanics. So this book by Anderson, or another book by Broek, or and the third one. So these are different books, 1, 2, and the third one by Prashant Kumar. So these are the books I feel are good for your fundamentals of fracture mechanics. So what we will discuss in this lecture is the rapidly propagating cracks, because as you know the dynamic fracture is different. Rapidly propagating cracks, we will discuss about that, and also their interactions. So what happens is this cracks generally occur. So dynamic fracture occurs due to tensile pulse generated by reflection of stress waves at free surface. Okay, at free surface. So this is as we know, we call it a spalling fracture or failure, when the tensile pulse will generate from the reflection. And then dynamic fracture is unique because dynamic fracture is unique because of the presence of waves. So that the difference between quasi-static fracture and dynamic fracture. So these presence of waves, there can be two source of these waves. So what will happen, suppose if you have a material undergoing fracture, let's say we have a crack here, and there is some loading from the top, let's say, and what will happen is the wave will generate from the loading, and it will come, this wave will travel from the loading due to the loading, and also some stress will be stress will be released from the crack tip as well, from this crack tip. So these are the stress waves. So first stress wave, I will write SW stress wave from the loading. So SW loading, and let's say SW, sorry. So the second one, we can write the stress wave from the crack tip. I will write just crack tip. So there are these kind of two kinds of stress waves can be there, and what will happen is some stresses can be travel back from the free surface, and that can generate tensile wave, and then these wave will interact with the crack tip, these waves will interact with the crack tip, and then what will happen is here what we are writing is the presence of waves from the loading and the presence of wave from the crack tip. Okay. So, these waves will, stress waves will interact with crack tip, and this will result change of crack speed, either change of crack speed or crack branching. That we have discussed about crack branching in our initial lectures. So, provided if intensity of stress wave is sufficiently high, if intensity of stress wave sufficiently high. So, this can change the crack tip, or crack branching can happen, that means multiple cracks which eventually lead to fragmentation. These dynamic fracture studies are important for different applications. So, these applications include let us say for crack arrest in engineering structures, these are engineering structures, and then fracture plane control in blasting. That means for some controlled blasting we can control the fracture plane, and then fragmentation in mining, and then military applications like fragmentation of bombs and shells, and then fracture of projectile dynamos, fracture of projectiles and armors, and then even space applications, so which also include like the impact of structures by meteoroids. So, these are the applications. For these applications, dynamic fracture is very important. The dynamic fracture knowledge is very important for these applications. So, that is why we are studying these applications. So, we will talk about now the materials background of the fracture. So, so there are three different types of fractures. So, here there are two brittle fracture mechanism we are showing here, brittle, and here is also brittle, but that is a different one. And the third one, this one is a ductile fracture. So, this one is ductile fracture. So, the first one we will go with the brittle, we call brittle transgranular, or sometimes it can be called as intragranular, intragranular fracture. I should write fracture here, and this one is called intergranular. So, fracture, sorry, probably I did not tell you these are the grains. I hope most of you already understood. So, these are the material grains. The grains are not exactly hexagonal, it will be a regular shape, but for our convenience we are drawing some hexagonal grains here with the same size and shape. So these are some material grains, as you can understand. These are for a metallic material. We are drawing these grains, and these grains may be in the micrometer level, let's say 50 micron or 100 micron. So now you have the crack here. This crack is going inside a grain, and this crack is dividing the grains into two parts. So that is called transgranular fracture, and this is another name of these is cleavage fracture. Cleavage fracture because it happens on particular crystallographic planes. Crystallographic planes, let's say mostly it happens in the BCC materials. Suppose some planes, let's say 111 plane or 110 planes, the fracture happens. That's why it goes inside the grain. But the other brittle fracture is intergranular. That means it goes along the grain boundary. If you see the grain boundaries, this is grain number 1 and 2, there is, let's say, then this is the boundary. So this is the grain boundary. So along the grain boundary it fractures. So that's why it is called intergranular. The other one was intra or transgranular, and the third one is called ductile fracture. So the ductile fracture, if you can see that there are some voids here, and then these voids are joined together. So what happens is here more energy are required. So I would write here, in ductile fracture more energy required for plastic deformation. So so before fracture there will be plastic deformation, so that's why more energy is required. So basically what happens is the tip of the crack, whenever you have a crack, there will be some, this crack will be blunt, and then ahead of the crack void will generate, and these voids will grow, and by plastic deformation, and then it will create a continuous crack like this. But because of the plastic, more plastic deformation in the brittle material, in the ductile material, and it needs more energy to overcome the new surface generation, crack surface generation. So that's why it is called ductile fracture, or it takes more energy than the brittle fracture. So in different materials, the fracture, if you see the micrographs, you can see clearly different brittle and ductile mechanisms. Suppose in the book, in Mark Mayer's book, you can see some micrographs where let's say aluminum alloy and pure iron, and which shows that at high strain rate loading, the iron got some these cracks, small cracks, and there are a lot of cracks. As you know, these are multiple cracks generates in dynamic fracture. So this is a brittle kind of fracture, and if you see in a aluminum alloy, this is the reference is actually Choquet. I think he took it from D.A. Choquet, SRI International. So for aluminum alloy there will be void generation, and some of the voids will come together, some will be alone, standing alone on the aluminum alloy. So these void generation shows it's a ductile fracture, and this basically both of these happen because of the spalling. In a brittle case, we can see that there are many cracks generated that is a unique feature of dynamic fracture. In quasi-static fracture there will be probably a single crack, not that many cracks, and even for the void growth and the ductile fracture mechanisms, you can see these cracks generated at many sites, the nucleates at many sites. So we will now talk about a little bit of fundamentals of fracture mechanics. So the stresses at the crack tip are much higher than the uncracked material that most of you probably have studied. So let us say you can imagine a ellipsoid, an elliptical actually elliptical hole this is. So this is used for modeling a crack, and if you see at this point the stress will be very high. So let us say assume that this is x2 direction and this is x1, and this distance half of the crack opening, this half of the crack opening is B, and this is let us say half of the crack length is A. So this is to model a crack with elliptical hole. So just to show you the high stresses here. So if you draw the y axis and as sigma, so what happen is sigma 22 in the 22 direction, the sigma 22 stress will look like this. This is sigma 22. If you see that, and near the crack tip it is as a very high value. It actually kind of a singularity. It's goes sharply up, and then probably the sigma 1 will look something like this, sigma 11. So we are more concerned about sigma 22 because that will open up the crack, this crack it will open up. So basically what is that is stress concentration at crack tip. So that means at crack tip stress is very high as compared to the uncracked portion of the material, and sigma 2 rises sharply around crack tip, that you can see from the figure. Now there is a parameter called stress intensity factor, which we will call as SIF, stress intensity factor, to characterize crack, to characterize a crack, I mean the potency of the crack, actually potency of the crack. So how potent the crack is to whether it will propagate or not. So this stress intensity factor is K, which is equal to sigma root over pi A. So what is this sigma and A are? As you know, the sigma are the stresses near the crack tip, and then A is the crack length. You can see crack length, half of the crack length. So how it comes, what happens is basically in the vicinity of the crack tip, the stress components are a function of sigma, the stress, and then crack length, then r, theta and geometry. So if we have a crack like this, so r means it at this position, this is r, and theta is this one, and then if we are talking very close to the crack tip, that means this r and theta, and even if we for a given geometry, these we can ignore, and then we can say that this is only a function of sigma and A. So R win this is the person who first defined this stress intensity factor. He proposed the stress intensity factor. So because sigma and A, two variable can be reduced by only one variable k, which is stress intensity factor. So it is something like, we use momentum P is equal to m into v. So for mass and velocity, we can reduce these two variables with a single variable called the momentum P. Similarly, the stress intensity factor, so what we can do is we can convert this sigma and A into one variable, then it will be easier for us to do the calculations. So I would write here, this is actually Ki instead of only K, because there are three types of crack opening mode. Mode 1 we call it the Ki, and there are mode 2 and mode 3. So this please you will study in a fracture mechanics book. So what happen is, so if a crack is opening directly, like what I can show you here in a tension mode, so this is called mode 1, and for mode 2 this will have a shear which is called in plane shear. So the one crack surface will move in this direction, let's say other will move in other direction, this is called mode 2, and the third one will be in the we call out of plane shear. So that is on the perpendicular to the plane of the slide, so that shear will be in the out of plane shear. So these are, please study these from a fracture mechanics book. So that's why we are writing here Ki, that Ki is the mode 1 stress intensity factor. So for different geometry of the crack or different boundary conditions, so what we can do is we can generalize it. Ki is equal to K sigma root pi A, and if Ki is higher than a critical value KIC, then the crack will propagate. So this small k is a parameter that depends on for different boundary conditions or different geometry. So here this KIC, this critical value, is called fracture toughness, and that is a material property. So now if you plot any stress sigma with A, so it looks like this, with increase of crack length, so stress required to propagate a crack will decrease, and so as we have a KIC fixed value for a material, so that KIC will be sigma critical into pi A. So what we did is, from Ki we had sigma equal to pi A. Now if you are talking about the fracture toughness, Ki is the stress intensity factor, that's a variable, and if it increases and exceeds this limit, then this fracture toughness we can define like this toughness. So as you can see that with increase of crack length, the stress required for propagation of crack will be lower. So we call this KIC as plane strain fracture toughness. Why we call it a plane strain? Because when you are talking about fracture on a very small thickness plate, that means if you are talking about the crack like this and your thickness of the plate let us say the thickness is very small, then the fracture toughness critical SIF value will vary with thickness. So, it will vary something like this, and then it will be constant at a higher thickness. The higher thickness that actually that is relative to the crack length. So, this is the KIC value, that is why we call it a plane strain. If it is for plane stress, that is small thickness, it's not constant, so it will vary. KIC values are different for different materials, that we can understand, and this KIC for metals are very high, they are very ductile material, and this value can be 20 to 150 megapascal I mean square root meter. So, this is for metal, and for ceramics, as it is a brittle material and then it has a lower fracture toughness, so that can be 2 to 5 only megapascal square root meter. So, however we have some mechanism to strengthen the ceramics methods for toughening the ceramic. So, this is the first method is fiber strengthening. What we can do is, there are some fibers we can give, some fibers we can give, and this is the crack. So, these fibers are ductile fibers, these fibers are ductile fibers, and these fibers act as crack arresters, they can arrest the crack. So, the fracture toughness can be increased, this we are talking about ceramic, toughness can be increased by 2-3 fold increase can happen. And then why it happens exactly, the reason behind is because energy is required to detach the fibers from the ceramic matrix. So, that is the additional energy required for from the ceramic matrix. So, as you know, otherwise they have very low toughness, but it can be a little increased with fiber strengthening. This is the number one method. Second one is transformation toughening. So, in this case, so there are some, let us say this example is the alumina, the entire material is alumina, and then these particles are zirconia particles. So, zirconium oxide, and these particles are tetragonal, it is tetragonal structure, tetragonal zirconia grains particles we are introducing. And what happen is with dilatation or shear these type of, we are talking about generalized general transformation toughening with dilatation or shear transformation, which is mostly in this case are martensitic transformation, due to the stresses in the crack tip as it is very high. So, some of these particles will convert to some other particles which has a different crystal structure. They are monoclinic, the same zirconia but monoclinic structure, same zirconia. So, these are monoclinic grains. So, because of the stresses at the crack tip, so what happens is the tetragonal that is actually called as a partially stabilized zirconia. So tetragonal, we can write P as Z, that is partially stabilized zirconia, can be converted to monoclinic zirconia, and in this transformation, so energy is absorbed. So in this process it is written that 4 to 8 megapascal square root meter fracture toughness can be increased. So that much can be the increase in fracture toughness, increase with these tetragonal zirconia grains introduced to alumina material, this alumina, and this is basically the stress induced whatever the transformation we are talking about is this one is stress induced transformation, and because of these applied stresses this transformation happens, and after this transformation actually relaxes the stress, and this will dampen the stresses, and that's why the toughening will happen. So the third process is third method to strengthen, or actually not strengthen, this mostly toughening we are talking about, toughen the material, is micro cracking. So these are some micro cracks here, micro cracks, if we can introduce micro cracks. So these will absorb energy, these micro cracks will absorb energy. So ultimately what will happen, the bigger crack, the major crack or bigger crack will take more energy to propagate. So this is also one way to absorb the energy and to increase the toughness of ceramics material. So that's all for today. So what we have discussed today is some fracture mechanics basics. So we talked about the brittle fracture and ductile fracture. So there are two types of brittle fracture we have talked about. One goes along the grain boundary, that is intergranular brittle fracture. The other is cleavage fracture, which goes through or inside the grains, that is transgranular. And then the ductile fracture, which absorbs a lot of energy because it allows plastic deformation, and the crack tips are blunt, and then voids grow in front of the cracks in that case. So that is for ductile materials. And then we have talked about the basics of fracture mechanics, again that the sigma is that stress is very high at crack tip, and combining the stress and the crack length, we have another parameter called stress intensity factor, which can be used to characterize whether the crack will grow or not. And if it grows, that value of the stress intensity factors exceeds a critical value, which is a material property called fracture toughness, then the crack will grow. And then after that we discussed about the ceramics. That ceramic has a low fracture toughness, but the fracture toughness of ceramics can be increased with the help of 3 toughening mechanisms. So we have discussed that. So this is all for today. So we will be continuing in the next lecture. Thank you.